Well, howdy there, Internet people. It's Professor Leach again. Today we're going to talk about the distributive property. Because the theme of this class is that algebra is arithmetic, so I really want to take a look at the things that we were programmed to do when we were kids about subtraction. And I want to remind you that we're not trying to look for a faster way to do these things. This is about flexibility and not about speed. So we want to look at what we're actually doing when we set up a subtraction problem. But if we want speed, if your argument is we shouldn't bother with this because we want to do things faster, there's a better way to be faster about math, and that's use a machine. So if I actually needed to know what 527 minus 248 is quickly, I would grab the machine and be like, oh, 527 minus 248. So that's what you should do if you want to do it fast. What I want to do is understand the arithmetic that we've looked at so far. How does it apply to something simple like this, even though we, quote, already know how to do this? I have no doubts that most people that we encounter already know how to do this. But I'd be willing to bet that most people we encounter don't understand what's going on. They're just applying a program that they were programmed with when they were a kid. And their brain was like a little sponge, and it was really easy to program them. That's why if you want to get a smoker, you got to get them when they're young and get them hooked early. So same thing with math. We're like, oh, let's just teach them tricks because they're children. And so you're like, oh, sit, and then the kid sits and you give them a cookie. And you're like, oh, good, stand, and then the kid stands up and you give them a cookie. And then you do the same thing with math, and then you wonder why they don't understand what's going on when they get to algebra. Mostly it's because your algebra teacher might not have understood this anyway as well. So this is not about speed, it's about flexibility, it's about trying to understand what's going on. And the theme is that of this whole class is that algebra is just arithmetic. We're leveraging what we already know about arithmetic and trying to apply it to new things like algebraic objects, specifically starting with polynomials. Let's take a look at this first. So just quickly, since I tend to ramble on a little bit too much, just quickly, the standard algorithm asks us to do things that I think are very strange. The standard algorithm, the usual, asks us to do things that are very strange. The usual algorithm asks us to do very strange things. I'm going to set this up in the way that we usually set it up, where we do a 527 minus 248. Does anybody recognize this setup? So go ahead and give me a thumbs up if you recognize this setup so this is us. We only add things that are the same, and when we add them, it doesn't change what they are. So here's us setting up the hundreds with the hundreds. In just numbers, sameness is place value. So hundreds go with hundreds, tens with tens, ones with ones. That's why we set things up this way, because that's how addition works. Now, the standard algorithm would have us do 7 minus 8 first, because the standard algorithm asks us to look at the most useless part of the number and figure that out first. So what is the price of this car? Well, the ones digit is a 9. So that's not helpful information. That's no good. So the standard algorithm asks us to do very strange things, and it asks us to say things that aren't true. In the standard algorithm for this, we would say the first thing we try to do is 7 minus 8, and then we say something that as adults we know is a lie. We can't take 8 from 7, so we need to borrow. Is anybody familiar with that? So the standard algorithm you can't take 8 from 7, So you have to borrow. I want you to realize that this is not just wrong on a factual level. 7 minus 8 is -1. So it's incorrect on a factual level. Let's see how it's incorrect on a moral level. So you have to borrow. They're programming you for an adult, as an adult, to be in debt. And they did this to you when you were a child. This is one of the most immoral things that I could think of that shows up in a math class. This is even worse than treating you like a computer. This is specifically setting you up to take advantage of you and keep you permanently in debt. So you can't take 8 from 7, so you have to borrow. You can't take 8 from 7. We know as adults that that's not true, because you'll be a student, you're like, oh, I have $7. And then the college will be like, oh, this class will cost $8 more. And you're like, oh, dude, I don't have that. And then the college be like, oh, you have to borrow. And off to the bank we go. I don't know if any of you are going in debt for this endeavor, but you should find another financial stream, because this is expensive. Anyway, so this is what I don't like about this. We have to take the 7 and we borrow from the 2, and we do 17 minus 8 and come up with a 9. So I don't like this algorithm. It starts with also we start with the least important part of the number. We're starting with the least important part of the number. Who cares what the ones digit is? Whereabouts are we going to end up? 500 minus 200, probably 300 something, or maybe 200 something, because the 48 is going to chip into the 300, because it's 27 and 48 is more than 27, right? So we want to think in those terms. 500 minus 200 is 300. Oh, but it's 48 and there's only 27 to start with. So the 48 is going to eat through the 27 and then take some away from the 300. It's 200 and something. That's just us looking at what's going on. Once again, if we wanted to do this fast, the problem's already been done. We already know that. So that's clearly not the point. What we want to do is when we look at a number like 248, it's actually telling us the digits, what the digits represent, 248. So we want to look at the 248 as a sum, but a sum with a bunch of place values. So we want to look at 248. We think of it as the sum. There's 2 hundreds, 4 tens, and 8 ones in place values. Think of it in place values. So then, if we think of it in place values, we get numbers that are really easy to subtract, because I just have to worry about the 2. I just have to worry about the 4. I just have to worry about the 8. So if I want to do 527 minus 248, I'm going to think of the 248. I'm going to do 547. I spelled 7 wrong. I'm going to think of 547. I almost did it again. And I put 47. $527. Okay. And we're subtracting a 200, a 40, and an 8. But in parentheses. So the way that I usually phrase this is I say, let's subtract in pieces. Subtracting 240 and 8 from 527 means subtracting a 200, subtracting a 400, and subtracting an 8. Subtracting 240 and 8 from 527 is subtracting a 200. It's subtracting a 200, subtracting a 40, and subtracting an 8. And so I usually refer to this as subtract in parts. subtract in pieces. I'm inconsistent in what I call it, so sorry about that. So I think of this as subtract in places. Subtract by place. So instead of trying to subtract all these things together, just do 527 and just do it in parts. Minus 200 is 327. I spelled 2 wrong. 327, because that was really easy. 5 minus 2 is 3. 27 minus nothing is 27. Then we'll go through and subtract the 40. 32 minus 4, and we'll just see 32 minus 4, that's 28. And then we'll go in and subtract the 8. And then that'll give us the 279 we're looking for. We take out 7, and then one more. 7 drops us down to 280. Take out one more, and we're at 279, which is what we know the answer is. So this is not what we're going to be writing, because if I ask you what 527 minus 248 is, I expect you to just write the 279. I don't necessarily, in that first assignment I totally did, but in subsequent assignments, I don't really want to see what's going on in between. I want you to be able to get at 279. Moreover, we're in a math class. We're trying to learn math well enough that we don't have to write all this stuff down. The point of being in a math class is to understand what's going on, so you don't have to write all this stuff down. That's where we want to be. So forcing you to show your calculations and writing all the steps that I decide you need to write down. Only write down the steps that you need to write down. And it's okay if you're writing down like, okay, 527 minus 248 is 327, then 287, then 279, and then just box that. Does that make sense? So this is not what we're writing, this is what we're thinking. This business here is not what we're writing, it's what we're thinking. It's really hard to scale up these little curly brackets. It's not what we're writing, it's what we're thinking, and it's based on understanding the distributive property. When we're subtracting 200 and 40 and 8, we subtract 200, and then subtract the 40, and then subtract the 8. That's just the distributive property. We can think of it as distribute of the subtraction. Which is multiply by -1. So a negative out in front is like a -1 times 200 times 40 times 8. So we distribute the -1 and just subtract each of the terms. Subtract by place value. Any questions? So the other thing to think about is this is just one way we can think what's going on in the problem. Subtracting by place value. Now, the algorithm earlier said you can't take 8 from 7, so you have to borrow. And we know that this isn't true. If you take 8 from 7, you have -1. So let's just allow our digits to be things other than positive or 0 and +1 through +9. Let's think about this in a different way. Carve out a separate thinking pad over here. If I want to do 527 minus 248, let's subtract by place value. 7 minus 8 is -1. 2 minus 4, this is not 2 and 4, that's 20 minus 40. 20 minus 40 is -20. Because 2 minus 4 is -2. And 500 minus 200 is 300. So our sum We wouldn't normally speak this number this way, 300 and negative 20, negative 1. But if we subtract those numbers now, we get 279. So 300, negative 20, negative 1. 300 minus 20 is 280. 280 minus 1 is 279. We don't have to borrow. We just have to understand negative numbers. We would all be better off if we just taught people about negative numbers early on. And we wouldn't say ridiculous, incorrect things like, you can't take 8 from 7, because you absolutely can. It's negative 1. And we wouldn't start programming people with, so you have to borrow, because we make money when you're in debt. Because that's just insidious, and dare I say, evil and exploitative. You're a bank, you have all the money. You're not helping anybody. You're making money on all these deals. You know what I mean? All right. Sorry, sometimes I tend to cast banks as the villain. I only cast banks as the villain because banks are the villain. I'm sorry if you're a bank. Actually, I'm not sorry at all. You're a bank, you're a villain. I'm not gonna apologize for calling you out for being evil and exploitative. Go buy another yacht. Any questions? The reason that I care about something like this, the reason I care about thinking of things like this, is that we need to upgrade from numbers to other mathematical objects. First of all, we want to think about numbers as 248. It's telling us that it's a sum. 248. We just got rid of saying and when we say 40 and 8. We just say 48. That and got squished out. It's like, let's not say that. But in German, they still have the and in there. 48. They say und. My German is terrible, but you get the idea. They still say 8 and 40. I don't know why they say it in that order. It's like the 4 and 20 blackbirds thing. Just say 24. That's how we do it in the modern era. You know what I mean? So why do I care about how you do your arithmetic? Like I said, it's not about just getting the answer for that one little problem. It's not about doing it fast. It's about upgrading to something like 5x squared plus 2x plus 7 minus 2x squared plus 4x plus 8. We want to see this subtraction of polynomials as the same thing that we just did. We're going to subtract a 2x squared. We're going to subtract a 4x. And we're going to subtract an 8. The nice thing is, when we're dealing with polynomials, we have this unknown base. The base is just x instead of a base 10, which is all rigid. And you have to follow things a certain way. And you can only use the digits 0 through 9 in all your places. So rigid and boring. But with polynomials are like, the base is x. And so if you have 5x squared and you subtract 2x squared, well, first of all, we only add things that are the same. And when we add them, it doesn't change what they are. So 5 of these things minus 2 of these things is 3 of those things. If we have 2x minus 4x, 2 minus 4 is negative 2x. And finally, plus 7 minus 8, those are the things that match here, is negative 1. And we get a number, or a polynomial, 3x squared minus 2x minus 1. If we look at these polynomials and let x be 10, I'm looking at 527 minus 248. And the answer was 248. 79. But when we subtracted by place value, the answer was 300 and negative 20, negative 1. The answer was 300, negative 20, negative 1, which in normal notation is 279. We want to look at these objects and we want to understand how they're put together. We want to understand how the objects are put together. The number 527 is 5 of these 100s plus 2 10s plus 7 1s. That's 5 hundreds plus 2 10s plus 7 1s. And if we think about these numbers as being base 10, that means that's why we're separating these out as 10s. These are all powers of 10. 5 times 10 squared plus 2 times 10 to the first power plus 7 times 10. Well, 2, 1, this must be to the 0 power. And if we're familiar with exponents, anything to the 0 power except 0 is equal to 1. These are what the numbers are based on. The place values represent powers of 10. Place values represent powers of 10. The terms in a polynomial are powers of x. So if I look at 2x squared plus 4x plus 8, powers of x. We usually don't write x to the 0. We just leave off that because x to the 0 is equal to 1. And we usually don't write x to the 1, we just write x. So for x, we usually just write for that, we just write x. And for the x to the 0, we just leave that off. I'll leave that off later. So we usually don't write x to the 0 or x to the 1. We leave off the x to the 0 because x to the 0 is 1. And we just write x for x to the first. Then the rest of them, they just get powers. Any questions? How's everybody okay? So what I recommend is that when you encounter numbers and you want to start subtracting them, try practicing just doing the calculation in your head before you resort to the calculator, if you want to get better at this particular skill. It's easy for us to kind of understand what's going on here, but what I want to do is separate what you've already learned. So you've already probably learned that you distribute the -1 and then add the like terms. And that's okay, because that's thinking of subtraction as addition of opposites. So I'm on board with that. But I want to emphasize the place value business with this polynomial. And I want you to recognize that place value business with the polynomial and the like terms is the same as the place value business that goes on with numbers and the digits of a number. And we want to leverage that understanding of place value in the calculations that we come across. So if we have, for example, our bank statement says $307.28, and we just spent $35.61. I had to come up with a number, and I came up blank. I'm like, another number. We can just start subtracting in pieces. 300 minus no hundreds, but the 35s is going to make us less. So 307 minus 35. So let's subtract the 30. So once again, this is going on in our heads. If we subtract just the 30, we'll be at 30 minus 3, or 27. And then we can subtract the 5. And then we could subtract the 60 cents. Well, the 6 is going to wipe out the 20 and leave a -4. So, sorry. And then 8 minus 0. And then subtract the 1 cent at the end. I think I went down the bottom. Oh no. So once again, this is not something that we would write out, because there are more compact ways to write this out. We're not doing this to be faster, because there are better ways to figure this out quickly. 307.28 minus 35.61. Oh, good, I got it right. Any questions? Now, I usually just go in order because it has to go in some order, but it actually doesn't matter. If we separate out these digits, it doesn't matter what order we go in. We could subtract the things that we find easy first. Subtract the 1 cent, then subtract the 5, then subtract the 30, and then subtract the 60. It'll still work out because addition is commutative. Any questions? 307.28. Well, subtract the 1. 307.27. Subtract the 5. 302.27. Subtract the 30. 272.27. Subtract the 60. 271.67. Once we're subtracting in place value, so this one was minus 30. I led with like what I identified as the easiest one, subtract the 1 cent. And then I subtracted the 5 because I'm just kind of subconsciously avoiding subtracting the one that's bigger. Oops. And then the last one, I'm like, well, I got to do it now. And then so the last one I subtracted the 60 cents. Subtract things in pieces. Understand that numbers are made up of digits, which represent powers of 10. We're going to expand this to cover polynomials. So we want to do the same thing that we do with numbers in polynomials. Any questions? How's everybody okay? Everybody's very quiet today. Good. All right. So that's that wasn't a thing. We didn't have like a group activity today. I know I advertised this as being a place where we work on group activities. We're still trying to build up some more, a stronger foundation. Remember the goal of thinking about algebra as arithmetic. We're still trying to reinforce the foundation of arithmetic that we were all programmed with when we were kids. I know you don't like to think of it being programmed as a kid, but if you were taught things like take 8 from 7, can't take 8 from 7, so borrow from the tens, you were programmed, and it was weird. And looking back, I want you to recognize that that programming was weird. Any questions? Comments? Snide remarks? All right, that'll do it for today. I'll see you all tomorrow. We'll be back to our original programming of exponents. We're going to be talking about exponents some more. And we're going to start making this transition into talking about polynomials and repeated addition, repeated multiplication, and the distributive properties. All right, so practice this kind of technique in your day-to-day lives. It's going to be slower, but it's always going to be when you're writing things down. It's always going to be slower than when you just use your calculator. I almost said your Cadillac. It's always going to be slower unless you're using your calculator. So anyway, it's just a thought. Y'all have a good day.
Thank you, Professor.